Well, here we've got ourselves a beautiful reaction rate problem where we've got a pretty simple reactant with one-to-one stoichiometry where some bromoethane, C2 means it's an F, and then we've got a bromine attached to it. You could call it monobromoethane, but that's redundant. If there's more than one bromine, you'd say di and also where they are. So we've got bromoethane reacting with hydroxide ions, 1-to-1, to make alcohol, ethanol, I should say, and bromide ion. Now, so there's the reaction. We don't have to worry about stoichiometry because it's a 1-to-1. The first question is determine the rate law equation and the rate law constant for the reaction from these data. In fact, here's our A. What is the rate law for this reaction? Well, we can pick that up pretty quickly and easily because we know that for any reaction, our rate law will be equal to a constant. That's very nice, being able to know about this. This will be good for a specific temperature, of course, lowercase k. So we'll have a number that we can calculate, that we can count on to always tell us about this rate. And then we're going to have to include the reactants. Now, in this case, I'm using brackets to indicate molar concentration. If we were dealing with pressures, we would use parentheses. And, what is this rate dependent upon? Well, of course, this constant, which is going to be pretty important. And then the concentration of the bromoethane. Here, we'll write that down. Close the brackets. And the hydroxide ion concentration. And I'm going to put that down here. OH. And again, minus, it's an ion. And that's it. You can forget about the products because in this reaction, we're just going forward, and it's going to be these things that determine how quickly this goes forward. So we're not going to deal with the products at all. So writing a reaction rate law is pretty easy because we're not going to have any products in it. So just the reactants. Now, we'll know that the rate, that's speed, is equal to a constant times something about this concentration and this concentration. But the trick is that there will be an exponent for each of these. And that exponent is what we really have to find out in this reaction. Because this exponent could be a 0, which means that the number becomes 1, the stuff's unimportant. Or it could be a 1, indicating that as this is more concentrated or less concentrated, our speed goes up. Or it could be a 2, a squared, where if this is more or less concentrated, if you square that value, it's going to be important. So that would mean that this reactant, if it was squared, would be very, very important in terms of making this reaction go fast or slow. So, we could guess these numbers and have maybe a chance of getting it right. Typically, these both won't be 0. But at the same time, it's not too bad because all you have to worry about is whole number integers. Now, occasionally you can get a half or even a -1, but those are quite rare. And you'll never get a fraction for a problem like this on the AP exam. So really, we don't have an infinite number of numbers here. In fact, it's very interesting. Why would this be either a 0, 1, or a 2? We'll deal with that when we talk about collisions because things only collide in multiples, which is the secret of reaction rates. So let's look at the data that we have here. Okay, we have some real pretty data. We've got a whole bunch of concentrations of the bromoethane. In fact, notice that they're multiples. That's interesting. And then we have some concentrations of hydroxide ions, not as much variation. And then we've got how quickly they occur, how quickly they disappear. This is the rate of how quickly the reactants disappear. Now, notice that they're very small numbers, and that's typical because we're dealing per second. For each second, how quickly are they going? So not much is going to change in concentration unless this is an explosion within 1 second. So this is going to be difficult to deal with because we're going to be comparing concentrations and rates. So let's make things equal. Let's make all of our initial rates have the same exponents, because we're going to be doing some comparing. And, if you've got different exponents, it's tough to compare things. Now, these first two are pretty easy. 9.6, oh, double. That's interesting. That's always something to look for. -5. And then here we have a -4, but we want to make that 10 to the -5 because we want to be able to compare these rates more easily. So this is going to be 14.4. All right, and then do the same thing here. You've got to be able to know your scientific notation, of course. And we're going to make this 28.8. So this is twice the speed of this one. This is twice the speed of that one. That's pretty obvious now, and it wasn't obvious before. And of course, we've got our concentrations here, 0.150 and 0.300 molar and 0.450 and 0.300. And then let me get these in quickly. I'll make that a 0, even though that hundredths isn't going to be that important. And here's where we have a little bit of difference, triple. Now, what we'll do is we want to see what happens when a reaction changes to its rate. Now, if you are good at looking at numbers like this and they don't intimidate you and so forth, fine, deal with this. But if these numbers seem sort of mystical to you, one thing you can do is just sort of simplify them. Do the same thing to everything. Instead of having 0.15 here, you can say 15, and you can say 30. It makes the comparison easy. 45, and then back to 30 here. This is a real simplification, but it might help you if you have difficulty with things and difficulty comparing numbers. Okay, 2, 2, 2, and 6. And here, well, I mean, if you really wanted to make things simple, in fact, I sort of will, I'm going to say 5. And here I'm going to say 10. And here, because I've been rounding up, I'm going to say 15. And then here, I'm going to round up to about 29. Notice that this is like super simplified. But again, we know these are going to be whole number integers. So a little bit of rounding here is not going to hurt us at all. Let's focus first on the bromoethane. Here we see bromoethane, and we see that it is 15 here and 30 here, which is doubled. Now, the important thing is I notice here the hydroxide isn't changed. So I don't have to worry about the hydroxide. This simplifies things. So I say 15 to 30, doubling. Hydroxide is not changing. So what does that do to the rate? You don't have to worry about the hydroxide. Just with bromine, well, the rate's doubled. Well, if the concentration doubles and the rate doubles, it means that this is important to the first order. Now we can double check that again. We can say 15 to 35 is tripling, and look, the rate tripled. So if this becomes 3 times greater, the rate, because we're multiplying by a constant, is 3 times greater. So we've got this part locked in. That's beautiful. Now the question is, what's the hydroxide going to be? Well, it's either going to be a 0, 1, or a 2. So let's see that. Now, we'll notice here that they didn't do anything to the hydroxides over here. They pretty much kept them the same except for the last. On the last one, they've tripled. We've got 3 times more greater concentration of hydroxide than we ended up having at any of these other trials. But look here, we had a 30 concentration with a hydroxide of 2 and a 30 concentration with a hydroxide of 6. So in this case, the bromine didn't change anything, but the hydroxide tripled. Well, let's look. Oh, here we have an initial rate of 10. And then when we triple the hydroxide concentration, we get like triple the rate. You can round these things off. So that must mean that the hydroxide is also first order. we got lucky on that one. We could have just guessed on the first case and been quite happy with our result. And so that's good. We've answered our first question. What is the reaction rate for this? What is the rate law expression for this question? We're set. It looks very, very nice. And so if this is the correct equation, you can take any two of these concentrations and multiplying times the constant, calculate this rate. That's pretty powerful. Oh, here's a question. What's the overall order for this reaction? Well, it's got two parts to it. First order with respect to the bromoethane, and first order with respect to the hydroxide ion. To find the overall order of the entire reaction, we merely add those exponents. So the overall order of the reaction is second order if we incorporate both of these substances, adding the exponents. But that incorporates both of them. Now, the last part of the question is, what is the rate constant? Well, we've got the equation. We figured that out. And we need to find out what this K is, a number that doesn't change no matter what happens. So if we know the concentration and of one substance, the bromoethane, and we know the concentration of the hydroxide ion, and here we know what the rate is. We know three of these four values, and we can just use algebra to solve this. So let's do the math on this and solve it. And as I say, you could use any one of these four. If your equation here is right, every one of these things will produce the same K. In fact, that's one way of checking to see if you're right. Well, let's see. All of these look about the same difficulty in terms of numbers, so I'm going to pick the last answer there and use that. The rate is going to be equal to, we know what the rate is. The rate is equal to 2.88 times 10 to the negative 4, is equal to our rate constant for this reaction times our concentration of 0.300 molar. I'll just write down 0.3 to save some ink, and some 0.6 here. We know this is going to be good to 3 significant digits anyway, and then I can solve for K. Okay, let's see what that is. Alexa, 2.88 times 10 to the negative 4 divided by 0.3 divided by 0.6.
2.88 times 10 to the power of minus 4 divided by 0.3 divided by 0.6 is 0.0016.
Okay, well, Alexa has got her answer there, 0.0016. I'll put a third significant digit in there. That's valid. And this is a rate constant, and it has to have some units. Now, those units have to be set up so that we end up getting molar per second. So when we're multiplying our K here, we end up having to have a per second. So we know it's going to be per second. I'll use a division rather times 10 to the negative 1. And also, we're going to have to multiply this K times molar. So we will need to end up finally getting an answer of molar per second. So in order to do that, we're going to have to say 0.0016 per molar second. If we have 0.0016 per molar second, if we have 1 molar second, and multiply it by molar and molar, we get a final answer of molar per second is what our rate should always end up being. Now, on AP questions, when you give a rate constant, you usually will get 1 point for the correct numeric value and 1 point for the correct unit for the rate constant. And in a second overall order of reaction, your rate constant is going to have molar per second in order to multiply out with these units to get molar per second, which is what the initial rate will always be. Well, there you go. This is the complete solution on an FRQ. This probably would be worth, my guess is about 5 points for these items. There'd be some more questions on the FRQ for it, but there you go. A rate law problem, all taken care of. Alexa, thank you for your help.
You're welcome, Peter. Enjoy your evening.